class. Let's continue with our lectures. We're now on Module 3, and Module 3 has been divided into 3.1, 3.2, and 3.3. And Module 3 is chemical kinetics. So we're starting with chemical kinetics. And we'll follow this outline: rates of reactions, measuring reaction rates, factors that affect rate of reactions, rate law, other molecularity of reactions, and then we'll conclude. Now, rate of reaction. Change in amount or concentration is given by the amount of the substance divided by time. And of course, that is what is given in equation 1. And if you look at equation 2, you see that we're now looking at a small change in x, where x is the concentration of the amount divided by a change in time. So if we look at a situation where you have a competition and 2-3 students are given 5 grams or 25 grams depending on the weight of the indomie, this indomie competition. They now cook food, cook the indomie the same quantity, and they are now told to finish it within a certain period of time. Now we're talking about the rate of consumption of that indomie. So the person who finishes in the shortest possible time has come first. So what that means is that what quantity did you consume within a particular time? The same thing happens in a race, 100 meters, 200 meters. Tell you that somebody has broken a record. If somebody did 100 meters in 6 minutes, so it means that the person has covered 100 meters divided by 6. So if you do that, you know what it means. The rate of that race will be the meters covered per second or per minute. So we're using an example: when acidified hydrogen peroxide is added to a solution of potassium iodide, iodine is formed. Look at that equation. So the concentration of iodine rises from 0 to 10 to the power minus 5 moles per dm cube in 10 seconds. So the rate will be change in amount of substance over time taken. That's 10 to the power minus 5 moles per dm cube divided by 10 seconds. And that's exactly the rate of that reaction. So generally, for a simple reaction, A to B plus C, or even A plus B to C plus D, now the reaction can be expressed in terms of decrease of reactant concentration with time or increase on product concentration. So recall that at the beginning of the reaction, the reactant concentration is high at the maximum, but product concentration will be 0 because the reaction has not started. The moment the reaction starts, the reactant concentration will be reducing, whereas the product concentration will be increasing. So that's why we have the rate of reaction. For reactants, we have a minus sign. The minus sign will help to now make the rate of reaction positive because the concentration of the reactant is decreasing. So our final concentration will be smaller. If you say final concentration minus initial concentration, you will get a negative sign for reactants. And that's why we have a negative here to cancel that negative. But for products, the final concentration will always be higher because at the beginning of the reaction, there won't be any product concentration. So for products, you have positive. That's why you have minus dA over dt, and it's also equal to plus dB over dt equal to plus dC over dt, where A is the reactant, B and C are products. Now, measuring reaction rate. We can measure the rate of reaction in the course of any reaction. The rate of chemical reaction can be obtained by following some property which alters with the extent of reaction or with the rate of reaction. So, if a particular property can be concentration, it can be color, it can be any particular property we're interested in. that changes. For instance, the color can change from light blue to deep blue and so on. And we can use any instrument that can give us, proportionality in color change as regards concentration for us to get the concentration of the reactant at any point in time. And once we're able to measure those concentrations, then we'll be able to measure the rate because we also know the time difference. Now, by analyzing the reaction mixture at suitable intervals, it is possible to determine the concentration of both reactants and products at different times. Hence, we'll obtain a measure of the reaction rate. So once we're able to get the concentration at a given time, we'll divide that concentration by the time, and that gives us the rate of reaction. Now, there are 4 methods usually employed. There are so many of them, but these are very elementary methods. Using titration, that is titrometric analysis, like the one you do in the lab. You do a titration to find the equivalence point. That is also measuring reaction rate. Colorimeter or colorimetric analysis. You use a colorimeter to check the change in color directly proportional to concentration. The same thing with conductivity meter, that is conductimetric analysis. And we can also use pressure measurements for gaseous reactants. Now, rate of reaction can be affected by several factors which have been grouped into this availability of reactant and surface area. Now, if there are no reactants, then automatically there won't be any reaction because the reactants must collide with each other, as we shall see in the collision theory. Before a reaction takes place, there will be bond breaking and bond making processes. So reactants must be there, and then their surface area. You find out that if you get a log of wood, ignite the log of wood, put it on fire. It takes time before that log of wood burns. Sometimes it takes days. When you come back, you see it still smoldering, burning. It takes quite a long time. But if you pieces that log of wood, you have increased the surface area. The moment you pieces that log of wood, automatically when you put fire to it, it will burn faster. That means increase in surface area also increases reaction rates. The second is concentration of reactants. Of course, increase in concentration also affects reaction rate. Of course, we are saying on the general, when we talk about the order of reaction, then the order of reaction also plays a very important role. Then, of course, light, there are reactions that require light. For instance, there are some reactions that can't take place in the dark. So light will have to initiate some kind of, bond cleavage, most likely homolytic bond cleavage, which will produce free radicals. For instance, chlorine molecule can be split into chlorine radicals by light, and that automatically, in fact, these are part of the reactions that take place in the troposphere. So light also affects rate of chemical reaction. Then again, catalysts. A catalyst also affects rate of chemical reaction. For those of you who take a higher level course, the 200 level course, we'll find out that the catalyst, affects rate of reaction or improve the rate of reaction by reducing the activation energy. We'll see the activation energy very soon. So once there is a reduction in the activation energy, the number of molecules that can go into products, into reaction, will increase. So catalyst also affects the rate of reaction. Again, temperature of reactants. Of course, we will see that change in temperature also affects rates of chemical reaction. In fact, increase in temperature increases the kinetic energy of the molecules. And when the kinetic energy of the molecules increases, then there is every likelihood that the molecules will increase in collisions, increase in bombardment, and increase in that bombardment will now also increase the rate of reaction. Rate law. Now, for instance, if we have equation 4, that rate is equal to K into X to power N. Now, when N is equal to 0, the reaction rate is said to be zero order reaction. That N, superscript N there, is the order of reaction. So when it is N, note that everything raised to power 0 is 1. So it means the concentration there will now be equal to 1. So that automatically means that for 0 other reactions, the rate is equal to the rate constant. So in other words, the reaction rate is independent of concentration of X. This means that changing the concentration of X will not affect the rate of reaction. Remember when we were talking about factors that affect the rate of reaction? I said that we're dealing with a general case, because when we talk about the order of reaction, then in terms of concentration, the way concentration affects rate of reactions will depend on the order of the reaction. Now, when n is 1, the reaction is proportional to kx to the power 1, and the reaction is said to be first order. That means an increase in the concentration would directly proportional increase the rate of reaction. Now, when n is 2, the reaction rate is proportional to kx to the power 2, and the reaction is said to be of second order with respect to x. So, which means the concentration, effect, or rate of reaction will depend on the order of reaction. And then this rate law is obtained experimentally. We said that the rate constant, K is the rate constant for a given reaction at a particular temperature, and the rate equation can only be obtained experimentally. So it cannot be deduced either theoretically or from stoichiometry. So you don't just look at the stoichiometry of the equation and then you start saying that the rate law is this or that. Of course, later we're going to look at how the method we can use to obtain the rate law, the rate constant and order of reaction, and of course the rate law for any particular reaction. Now, order and molecularity of reaction. We have mentioned order of reaction when we said rate is equal to kx to the power n, where n is the order of reaction. So if we use a specific reaction, A plus B giving us products. Now the stoichiometry of A is m and that of B is n. So the rate will be equal to K, concentration of A to the power m, and concentration of B to the power n. The indices m and n are known as the order of the reaction with respect to A and B, so that the overall order of reaction will now be m plus n. So the order of reaction with respect to given reactant is the power of that reactant's concentration in the experimentally determined rate equation. Remember, it must be experimentally determined. The overall order of reaction is the sum of the powers of the concentration terms in the rate equation. Molecularity is applied to elementary reactions or the elementary stages of a more complex reaction. There are certain reactions that are elementary reactions that just go, from reactant to product. But there are some reactions that are complex reactions. Complex reactions will have, different stages. For instance, if somebody is moving from Uturu straight to Okigwe, then that becomes a very simple movement. But somebody who wants to go to Uturu can move from Uturu, get to Ihube. From Ihube, he now gets to Ako. From Ako, he gets to Omololo. From Omololo, he gets to Okigwe. Now that is a complex reaction. When you now come down to check, you will find out that he will have different disturbances along that road he has taken to Ihube, to Ako, and all that. That is a complex movement. But when it comes to a simple reaction, then we'll talk about molecularity as the number that makes up the activated complex. That is, if there are two molecules that react to go into activated complex before the reaction takes place, we say it is bimolecular. If there are one molecule, we'll say it is unimolecular. So for complex reactions, we must first of all break it down using the mechanism to know the simple reactions that make up that complex reactions. And then in the elementary or simple reactions, we can now talk about the molecularity. And we said that molecularity is nearly always 1 or 2, but sometimes it can be 3, but it's very rare. But it's difficult to find molecularity that is 4. It's just like where people are fighting. It's easy to see two persons fighting, each other. So sometimes it becomes difficult for 3 or 4 persons. If they become 4, they will automatically split into 2. This one will be fighting the other one will be fighting the other one, which reduces to 2. So molecularity is either one molecule, which is unimolecular, or 2 molecules, which is bimolecular. Sometimes It can be trimolecular, but very rare. But it's difficult to get, molecularity up to 4 molecules. Conclusion of this module 3.1, we looked at definition of rates of reactions. We looked at how we can measure reaction rates. We looked at the factors that affect the rate of reactions, and then looked at rate law, order of reaction, and molecularity of reaction. So we expect that if you're asked a question on these topics, you should be able to get them correctly. Thank you very much, and see you in the next class.